All right, well, it says I'm recording, so hopefully this works out. First off, today in lab, we are going to be doing project 1, not lab 7. It's pretty straightforward, pretty easy. It's a great introduction. It's a really interesting introduction because it will help you learn about computer architecture. You're building up like the basic block of how computers start to think. Pretty useful, pretty interesting. I don't think it brings in anything that we don't know yet, but we'll talk about a little bit of stuff that is some review, some new today, starting off with some common components. So the first component that we're talking about, we're going to be in chapter 11 today, for those that like to follow along in this book. The first thing that we're going to talk about is called a comparator. Now, this term is interesting. So I come from strongly an analog background. The symbol that we use for a comparator in the world of analog is this. All this comparator does in the analog world and the digital really is ask the question, is A greater than B? If A is bigger, it outputs a 1. If A is not bigger, it outputs a 0. Now the book uses what we would say an overloaded term for comparator, where their comparator is checking for equivalency. So if A and B are equal, it outputs a 1, otherwise it's a 0. So their schematic symbol that they use is just a block. And you might have some number of inputs, so they're going to have 2-bit inputs with the output. And if this array is equal to that array, you could output a 1. So comparators are useful things. They are the fundamental block, essentially, of analog to digital converters and digital to analog converters. They convert both ways because you just need to know if something is greater than or less than equal to. So keep that in mind as we go forward. We may bring it back into some of our examples. This book then brings in the idea, the next section of this chapter, the idea of XOR gates, which I have mentioned before this, right? So the XOR gate much like the OR gate is 0 if neither, 1, 1. The difference between the XOR and the OR gate is XORs don't have that one, right? Covered this before, reminding this because this becomes helpful to us in just a moment. Recalling that you have this symbol. Oh, why did I just do that for? A XOR B, right? And this is equal to that. XOR this. Okay. And that's just because you have A and not B, or not A and B, right? Those two. Okay. Make sure I'm not worrying about too much of this yet. So they're going to bring in this book, they bring in some VHDL if I'm trying to do a comparator. And it's just asking, you can do simple statements like, they use this really awful notation, but we're just going to do this test is equal to 1 when boom, I made a comparator, right? This is just saying test goes high when A and B are equal, otherwise it's 0. That's all it takes to build a comparator, right? This matters in just a second, and we're about to get a little bit mathy. All right, so we recall adders, right? Where we have a full adder with 3 inputs, A, B, C in, and an output sum and C out. What we want to do is take use of some of the things that we just talked about that make adders better. Because we have this issue, right? When you have an adder, you want to either, right, there's trade-offs. You want to either be fast or you want to be size optimal, right? So we're going to talk about optimization. Which do you want? Do you want to be good on size or good on speed? So what we've done previously is something that is size efficient, which was the ripple carry adder, where you chain adders together, where you're going to have a C in, C out. The C out plugs into the C in and then calculates sum at 1. This is sum at 0, right? So this is, when I start sticking these together, if I want a 32-bit adder, I need 32 of these blocks. If each of these has 2 gate delays in it, which is reasonable, 2 or 3, then I would need 2 times 32 gate delays in order to do this addition, right? So this is pretty size optimal because each of these blocks is not very big. It's just a couple of gates. But it takes a long time to ripple down to a 32-bit adder. We don't want to wait that long time. Sometimes we want to add things together quickly. So what we're going to talk about starting now is something called a look-ahead adder or a fast adder. And the general idea on a fast adder is simply that you can know ahead of time if you're going to create a carry, right? Simply by knowing A and B, essentially. And there's another idea of propagating a carry. So if a carry comes in, will it carry on through? So that's the 2 ideas, generate and propagate. And we can calculate this just using essentially XOR gates and OR gates really quickly. So it helps us to recognize that we can define, let me draw up a adder table here so that we can keep this in mind. Okay, I won't finish the whole thing, but right, so the sum is going to be 1, 1, 0 with a carry, 0 with a carry. Right, so nothing adds to nothing. If I have a 1 or 3 ones, I have a, well, 1, I get a sum. 2 ones, I get no sum, but a carry, right? Because 1 plus 1 is 1, 0. Okay, and then 3, I get 1 plus 1 is plus 1 is 1 and a carry. Okay. It turns out that the carry out can easily be represented by let me make sure I do this right for a second. A and B. And that's if I am generating a carry, right? So this is like a half adder, saying the only way that I generate a carry is if I have A and B. If I want to propagate a carry, it's a different equation I'll get to in a moment. Thinking the same way, the sum, or I'll try to sum, can be expressed as, and I think one of the homeworks asked you to prove this. Maybe we haven't gotten there yet. It's just XORs of A, XOR B, XOR C. And you can actually get that from this truth table. So I'll leave that to you to prove it. For now, I just need you to believe me that that's true. It's some fun math to figure that out, and you use the XOR equivalency to solve that. So if I have C out as this, and I simplify the sum down to a half adder. So let's say, again, with the sum, I only want to worry about generating a carry, right? So this is propagating a carry. This is worrying about generation. Okay, so let's define this more explicitly. I generate a carry at a given fast adder location. So right, we're adding bits together. I generate it at a given location if I have A and B at that location. Generate a carry. I propagate a carry at a given location with A XOR B at that location. Now what I can do is look ahead in anticipation of if I'm going to carry or propagate. Now the math gets really bloated, and that turns into big, fat, complicated gates. But let's talk about the math first, and I'm going to rewrite these guys up here out of the way. So let's consider the first gate and its carry out, right? So the carry out in our first gate is just tied directly to whether we have a carry in or not. And this is what, if you're stitching multiple of these fast adders together. The carry number 1 then has an additional idea because it might make its own carry, right? So now we might generate a carry. So this is tied to the first input. This is, does the first adder generate an output carry? So do I generate it, or do I propagate it from the input? Right, that's the way I get a carry, is either I've generated it or I propagated it through. There's no other way to get a carry. On to the next one. Well, now it's getting more complicated, right? Because now I have, well, I could carry in, generate or propagate, or, well, again, this guy can generate it, or number one could propagate it and generate, or you could prop one, prop zero with a carry in. The carry in could propagate, or generate, propagate, or generate. Keep going. C3, G2, or P2, P1. P2, G1, or P2, P1, P0, or P2, P1, P0, Cn. Right? Now on to the next state. It can generate. The previous one could propagate with a generate, or two propagates and generate, right? So this is starting to get some complex math, but it's just repetitive. There's nothing, well, I shouldn't even say complicated, right? It's just a lot to it. But because of this, I can use the fact that I know ahead of time what my carries are going to be, right? As soon as I have my inputs, I can use these gates to calculate what my carries are going to be. Once I know what my carries are going to be, I can calculate the sum. So this fast carry adder uses that logic to generate look-ahead carries to quickly calculate it. So the first thing that has to happen is we want to create propagate, and generate bits. Phase one. Step two, you can go on to then create all of that next tiered logic, right, which is the ands and ors. So in the case of P3, say, for propagate 3 and generate 3, you need 3 AND gates. Where this is going to be generate 3, right? Because the generate 3 stands on its own from that earlier equation. And then you're going to have the G1 and P2 from the last one. And then you would have G0, P1, P2. And so on and so forth, right? So I'm just implementing those equations earlier in AND and OR gates. And that outputs me with the carry. So I have a propagate bit, generate bit that is used to calculate if I have a carry or not. And then we can use that simple XOR that I talked about for the sum. Because I know what A3 and B3 are because they're inputs. Carry 3 is calculated by propagate, generate, calculate, and fed there, giving me sum at 3. So in as simple as 1 gate delay, 2, 3, 4 gate delays, I have all sums. The trade-off being that this circuit gets big very quickly, because this is the gate for just 3 inputs. And every time I add a sum bit, I add another AND gate, and each of the cascaded AND gates get 1 more input, which makes them bigger, right, by 2 transistors. Any questions? We understand this idea of generate and propagate. Okay. Now there's one additional challenge to this. If I want to stick multiple of these gates together, or not gates, adders together, fast adders. So let's say I've made an 8-bit ripple carry, or fast carry, sorry. I can stitch them together, but I need to generate a carry out from these. And there's an equation for that. I'm not going to write it because the carry out is just another big mess like this of the next step, right? Because the carry out is the same, the final carry is the same as the carry out. So it really just adds 1 more mess of gates, and you now have a carry out, and you can stitch them together. The downside is if I want to make a 16-bit fast carry, the last carry out doesn't generate as quickly. It's the last thing that gets generated. Not really a problem. You're still going much faster than you would if you were using a standard ripple carry instead of this fast carry. So fast carry, big takeaway, it goes faster at the cost of area and complexity. If I built it as 4 bits, it propagates 4 bits at a time, therefore it's 4 times faster than a ripple carry. This book talks about standard logic chips. I'm not going to cover that. You go out, buy a chip, they have fast carry adders. They exist. Now the nice thing is, and if you take 3610, you'll come to understand a little bit more why we care about this theory, and we talk about it. But the nice thing is we have VHDL, right? And I could write that fast carry as gate level commands, right, structurally. I can say this and write out those equations. Or in VHDL, I can do something as simple as right? I can just add things together. If I wanted to be more explicit and call it a gate level, right? So sum we know is just the XOR of A, B, and Cn. And C out is, we get a carry if we have A and B, or A and C, or B and C. Ta-da, I've made an adder, right, in VHDL. VHDL is really nice. It makes life simple to implement either structural or behavioral adders. Need to be careful. If I'm adding, say, 2 bits to 2 bits, how big does sum have to be? 3 bits. It has to be 1 bit bigger because you have a carry out that you can store there. Or you could write a carry out expression, but just make sum bigger and ta-da, you're done. What that might look like. So I write in shorthand as I do VHDL up here. So I don't like write out architecture. I'm going to miss like semicolons all over the place. I might miss parentheses. This is mostly conceptual. If you have questions on the details of it, go ahead and ask and I'll fill you in because I can generally answer those. But it just simplifies things so we don't waste our whole lives watching me write stuff down. So let's make an 8-bit adder. Architectural behavioral of 8-bit adder is, and let's start by creating a signal. That signal is going to be called T of standard logic vector, and it's going to be 8 down to 0. For down to, I have started writing a down arrow, so we're all on the same page. It saves us some time. Okay, so it's a standard logic vector to 8 down to 0. It's 9 bits. We're going to add 8. I need 9. That's my output, right? Okay. Then I say begin. Begin. Architecture. Declare any signals and components that you might need, and then you say begin. Declarations. Behavioral. Okay. Then it's just a matter of saying this signal T is going to be, well, let me write it and then I'll cover through it rather than talking. Okay, so what this is doing is concatenating a 0 onto A. So it's just throwing a 0 at the beginning. It's just a placeholder. It's waiting to be added into maybe. And then it's doing the plus B plus C in, right? This could add up to 9 bits. Then C out, the carry is just that 0 that may or may not have the 1 that spills over into it when I add it, right? So I take that T at 8 and call that C out. And then the sum is just what's left, 7 down to 0. There's not really a difference between having a 9-bit sum instead of a sum and a carry out. Either way is really quite okay. Because it's the same thing, right? A carry out has the same value as the 9th bit at that sum. Any questions on that? So you can do this type of adding to certain types of logic, right? I cannot add bit vectors. I can add standard logic vectors if I'm using types unsigned or signed, right? So from those, if I'm importing, say, IEEE, the unsigned library, right? I also tend to use the numeric standard library. This one has troubles adding those sometimes. So just be aware the type that you're using, whether it's signed or unsigned or numeric standard, each of these could cause you addition issues when you start building something like this in what we call an ALU, which is an arithmetic logic unit, which is what project 1 is all about. Okay. Those adders. There's another device that is very important to all digital design called a shifter. Now, one of the easy and obvious ways to do shifting, or reasons to do shifting, is if you take something like this, right? Let's say this is a number, and I shift it this direction, and now I have what mathematical operation is that equivalent to? Yeah, it's multiplication by 2. Just multiply it by 2, just shifting it. So shifting can multiply as long as you're operating in 2s. They can also be worked as memories, where you can start storing up them and then shifting them out to use them. There are multiple ideas of shifters. So in this one, we would call it a zero fill shifter, because as I shifted, it filled with zeros. Other types of shifters is something called a sign extend shifter, which is helpful in signed operations to keep sure that they're stay the same if I shift them in different directions. Let's see what other ones they want you to know about. Yeah. They mentioned one called end around barrel shifters, which we don't do much with. End around is if I had this one and I shifted it left, this one pops out this side and comes back in the other side. Those are really good for like pattern generators. Mostly we're going to focus though on this one, the zero backfill. So let's make a shifter in VHDL. So this is just me throwing what we would call combinational logic at you, and then showing you how to make this in VHDL. So you see lots of VHDL examples of what we would call simple devices. Okay. So all this is saying is, let's assume that I have some input S that tells me how much I want to shift it by. Now I need to make sure that S is an integer. So I can use this command called convert integer. So K is S turned into an integer. Then this is a concatenation operation, right? We've talked about that. It's an important idea. It's just sticking two things together. It has this O output where it's taking K down to 1, throwing zeros in, and concatenating with the input from 3 down to K. So I keep the input and concatenate, or well, I keep K bits of the input. Okay, so preserve K bits, shift it, and then pad a whole bunch of zeros. In fact, K zeros. That's a shifter. A zero fill shifter, specifically. We could also make it like a one fill shifter doing various other things. They do in the book on figure 11-18 show you various types of shifters and their implementations. I do suggest looking at them. So they have like a shift right with sign extension. They have shift left with backfill. They have shift right end around and shift left end around. So shift left means it shifts left and goes wraps around. Shift right is right and end around, right? You'll also notice, I don't know if the book tells you this, as long as you import the correct libraries, you can just do this. Shift left, shift right. Those are viable commands with the unsigned and signed libraries. And I think numeric standard. Okay. Any questions up to this point? If I ever go too fast, let me know. I'm trying to make sure I go slowly enough because I know VHDL is new and overwhelming. We're going to move on to section 11.4, where we're going to, lucky you, talk about arithmetic logic units, which is what our project is about. So you're going to get a nice introduction to this to prepare you for later today. Okay. So an ALU is the idea where you're going to take adders, subtractors, what else are they putting in there? Complementing and various functions and putting it into one block. And then you're going to be able to pass a command to this block as well as the inputs and get the result that you want. So functions that you might have, right, are like add, or add with a carry, or subtract with a borrow. It also uses negate or complements. So negate is turn negative, right? And complement is change a 1 into a 0. They're different things, and you need to keep track of those. You might take operations. You might tell it, I need you to do and these, or these, or XOR these. You might have commands like shift. So that's what an ALU is doing, is it's this one block that takes things and builds them together. Now, we have a schematic symbol for an ALU. Okay. So these slashes through lines is the book's notation for what we call a bus. So it may have more than one bit. If it has a slash through it, there's more than one bit stored in there. We don't know. The book's notation is they do /n. So it has n bits. It has a carry in, a carry out, and then last but not least, it has an m input, which is command. What am I supposed to do with inputs A and B? And then it will output it. So the ALU itself, man, this lecture went really quick. So is, sorry, just lost my train of thought. It would be difficult to draw gates, right? Because I've drawn the adders, I've drawn subtractors, we've talked about all of this stuff, and it can do all of these operations. What we want to do is build up each of these blocks individually, and then select from the output, the proper output. So you can do all of the calculations in parallel, and then just choose which operation you want the output of. What device do we have that allows us to choose one of many inputs? A multiplexer, right? So I can just build this up as inside and say, I have an adder, I have a subtractor, and I have a multiplexer, and I get to choose which of those outputs that I have. So to build an ALU in the bluntest way possible is to just build an adder, build a subtractor, build everything that you need, and then have a muxed output. Does anyone see the obvious downside to doing it this way? What's a potential downfall? Power. I am doing the add, subtract, and every other operation all at the same time. So no matter whether I want them or not, they're consuming power. So you could build up a more complex logic that saves power, but then you're adding space, right? So only add if, so on and so forth, but it costs space to do that. After figure 1121, I really wish I had page numbers that matched your guys, but I don't. There is this idea of function codes. So M that comes into here, right, can't be a word. It's going to be, say, F code. And you assign function codes like this. Your function code assignments are going to be your choice, I believe is what the project says. But you could have something like where function code 00 adds them together. So if I put 00 on M, it comes in here, and M selects 00 of the mux and outputs the addition. Okay, so that took way less time than I thought it was going to. We have 30 minutes left. Now, this is actually not a bad thing. You guys, if you would like to ask me questions about VHDL or your homework or any of that, I'm open to questions. If you're watching on video at this point, I will leave it recording. I don't know how this will go, if it'll be boring. If you want to turn it off and then just email your own questions or office hours, it's a good solution. Yes.
For the homework due today, I had a question on 9, problem 9.
Okay, what's the question?
It says show how to make a 2 to the forward line demultiplexer using several 1 to 2 line demultiplexers.
Okay.
And I just don't really understand what a demultiplexer is.
Okay, so a multiplexer, is it D or multi? D. Okay, so a demultiplexer is just going the opposite direction. I hate the books. The book only draws a block. I have always seen people use a demultiplexer just drawn in the opposite direction. Whatever, I suck at drawing. Where I have a select 0, a select 1, and an input, right? And that input will go to one of these 4 outputs. The other 4 outputs will be held to 0. Now it's asking you to build this with just these.
What does it mean by a 2 to 4 line demultiplexer? Like 2 to 4 out. So you're taking 2 ins.
Yep.
To 4 out. So 2 ins. Like I understand getting 1 in and 1 out, but 2 in, 2 out, or 2 in, 1 out.
Can you read the full question for me?
So it says show how to make a 2 to 4 line demultiplexer using several 1 to 2 line demultiplexers.
2 to 4. I mean, that is a weird way of phrasing it. Ah, do you know what it probably wants?
So what is the 2 to 4 mean? 2.
This is 2. 2.
Wait, that's 1.
So I have your answer. So what it wants, I would imagine, the only reason I could picture doing this is that your 2 options are those connections or that connection. So you're taking a bus of 2 bits and attaching it to either this bus of 2 bits or that bus of 2 bits.
Okay.
So they won't be connected?
These 2 will never connect.
So like I understand how to do like that. Like it makes sense in my mind when I do like a 1 to 4 demultiplexer, but when it throws in this like make something 2 to 4, it's like I can't really like understand how to do that. Like I don't know, I just look at the question, I'm like I understand how to do like a 1 to 4, but how would you do it 2 to like what? How would you do what you just drew right there?
How would I do what I just drew?
Yeah, how would you make that out of 1 to 2 line?
Okay. Well, it's not that difficult if you break it down into components. So you know that you need a 1 to 2, right? You're going to use multiple of those.
Right.
In VHDL, when given buses of things, which all this is a bus, if I redraw this, and depending on your schematic, you may end up with the line, or the other one is they make them really fat. Hand drawing, that doesn't work as well, but I will attempt it. Oops, that was like really fat. Okay. If I draw that, right, this looks like a 1 to 2, right?
Right.
How many selects do I need?
1.
Yep. Does this give you a clue of how to start building that?
So the bigger the line is, that just means that there's multiple inputs and outputs.
Yep. Yeah, this is equivalent to drawing by the book's notation. Do any of you see how this gets implemented?
One to two multiplexer with two hits, and then you put this and this up.
Yeah, essentially, this or that is no different than two 1 to 2 multiplexers in parallel.
So it's basically just like having, yeah, like two 1 to 2 multiplexers, but they're not connected.
Yep.
That's it.
Yep, they're not connected.
Okay.
The only thing that might make this complicated, which I'm not going to because it doesn't specify it in that question, I didn't write the book, is you may be in a situation, which I don't believe this is a real situation, where you also want that selection. So there might be some crossover, but that's not particularly difficult to implement either.
Yeah, that's just the one that was, so.
Yeah.
That helps.
Right, because and if I wanted to make this connection, then it's just two 1 to 3 muxes. Because now there would be 3 locations, right? So this guy could connect to 1, 2, or 3.
Oh, yeah.
And then this guy could connect to 2, 3, or 4. And so I stick two 1 to 3's multiplexer, and now I can select that. But I need 2 select channels if I do that. Yeah, so I assume in this exercise, the point is to hammer home the idea that VHDL and digital circuits work very well as modular components. So you just build them up with little parts and then piece them together as puzzle pieces. Other questions? You guys are doing okay in Vivado? Has anyone tried doing the EDA playground that I talked about in lab?
I tried to do it, but I couldn't make a test bench, so I just downloaded Vivado on my computer. So it was just EDA on that thing online is just like way more confusing than I thought it would be. I don't know. I just.
Yeah, so I haven't done much with it. If anyone, this includes video people, can't get access to Vivado at home, especially, reach out to me and I will find a good tutorial for you to look through on those. It is not what I would call a good solution, but it is possibly the only working solution that I could think of if you can't get Vivado. Should the apocalypse continue to happen, right? So we don't want you guys to end up stuck at home not able to accomplish this. Like, I really do want all of you to succeed. I want to see all of you in my 3610 class next semester or a year from then. Not next semester, next year. So we'll offer 3610 in the each fall, we offer 3610. Your choices in this program are apparently between 3610 or Power. I strongly advocate for 3610, which is digital systems, over Power for many reasons. And if you are on the fence and aren't sure what you're doing, come talk to me and I can explain why going into Power is a bad idea. Part of it is because they don't pay as much. All right, questions? Yeah.
I have a dumb question, but what's the best way to get our homework into like a single PDF so we can submit it?
Okay, so it depends. On one way that is pretty good to do, that I like to do, is you can put it all into Word, and then just you can save it as a PDF or print it as a PDF. That's a pretty simple, straightforward way to do it. The other way is to print it out, and it's built into iPhones, and you can download, I think it's called Cam Scanner for Android. And you can just take pictures of them, and it will auto crop around the paper, and then you can build a PDF out of that. It's not a dumb question. Everybody struggles with it.
And with making those, like you just want nice like screenshots of the code, the snippet.
As long as the screenshots are clear, so you take it using the computer. Don't put me screenshots that are from your cell phone that then you email to yourself and then paste it. Don't do that. The screenshots are okay, as is just copying and pasting the code. Yeah, I was going to ask for the VHDs, but it turns out Windows views VHDs as hard drive disk images, and antivirus does not like those. So sending VHDs to each other is really difficult. So if you ever end up sharing code with people, it's really easy just to rename to .txt and then send it, and then they just rename it to .vhd. Yes.
On the last point, it tells you to draw a block diagram. It's just a piece of picture.
Yeah, so a block diagram is this thing that I draw for you guys all the time, where I'm like, right, this is a block diagram. These are a very useful tool, and you will use them all the time.
It is on the lab, by the way. But I didn't take a screenshot of that little file. Make it okay.
Sorry, say that one more time.
You can get it on the lab, and nice, just cut the picture and put it back.
Yeah, but I recommend drawing it, because if you do it, it helps you remember. Because I could ask you on an exam to draw me a block diagram of the VHDL system that does blank. You don't need to do any VHDL, just show me the block diagram. That could be a question, right? And that would show me that you know how to build up circuits together without taking all the time to write VHDL on an exam. Drawing block diagrams is really a good way to start a lab or a project, because it starts making you think how they're connected together and how you might build them. If you're ever having struggles with something like the mux, start drawing muxes. As I said, if you have using 1 to 2 demultiplexers, build this. Start by drawing a 1 to 2 multiplexer, drawing the connections that you think it should. And if you're, say, in an exam or something, and you don't know what's going on, and you just start drawing blocks and sticking them together, I can at least give you guys partial credit because I can see what you're thinking and give you points for the effort, right? Because a lot of this class is starting to get you guys to think logically, procedurally. How do you build up systems from nothing? If everybody is satisfied, no more questions, you can go. But I will hang around for another 15 minutes to answer any additional questions. I will do something similar to this, a short lecture on Wednesday, and then I will hang out and help you guys with code. So if you bring a laptop and have started the project, it would be very beneficial to you guys. I mean, we'll start the project this afternoon, right? But the more progress you make, the more helpful Wednesday will be. And I will try and figure out a way to bring in Zoom callers, I think, on that. So if you can't make it to class,